Hello, everybody. Thanks for coming today. So like Nick said, I want to talk about using neural networks to model sequences. So in the last lecture, you saw how if we have a bunch of independent data points, we can fit a neural network model to model those data points or examples. But what if each example itself consisted of multiple data points, and those data points were somehow related or dependent on each other? So this is the key idea of what a sequence is. And the sequences can be something like a sentence, where a sentence consists of multiple words, and each word is dependent on other words in the sentence, or something like a function or a speech waveform. OK, so you've encountered sequence modeling tasks probably in your everyday life if you've used Google Machine Translate or Alexa or Siri. Things like machine translation and question answering are all sequence modeling tasks, and the state of the art in these tasks is deep learning based. So I want to talk about how to model sequences and start off by motivating why we need a different framework to model sequences. So let's just say, from what you know so far, if we have a feed-forward neural network and we want to model something like a sentence. So we know that we need an input vector to feed into that neural network. And the other thing we know is that we need to specify the number of input nodes. So that input vector has to be of a fixed length. So now let's say we have a sentence, and we want to transform it into a fixed length feature vector. Our first idea might be to represent this sequence as a bag of words. And all a bag of words means is that we have this fixed length feature vector. Each slot represents a word, and the number in that slot represents the number of times that that word happens in the sentence. And then now we have our fixed length feature vector, and we can feed that into a model and make some prediction, like whether this sentence is positive or negative. The problem here that you might notice, though, is that there's no order preserved in this representation. So let's say we have these two sentences. The food was good, not bad at all, and the food was bad, not good at all. These have completely different semantic meanings, but in their bag of words representation, they would be exactly the same because they contain the same set of words. So this is clearly a problem if our network isn't able to distinguish between these two sentences. So we know now that we want to kind of preserve the order of our sequence. So now the next thing we might think of is to just make a longer feature vector in which we allocate space in the feature vector for each word in the sentence. So now the first 5 slots in this vector correspond to a representation of the first word. And again, now we have our fixed length feature vector. We can feed this into a neural network or even another machine learning model and try to make a prediction. But the problem we might notice here is that each weight connecting each one of those input values to the hidden layer is calculated, is a separate weight. So it's going to make it really hard for us to deal with different word orders. So let's look at these two sentences. On Monday, it was snowing versus it was snowing on Monday. Now, these mean the exact same thing, but if we look at their representations, they're completely different. There's no overlap. So it's going to be really hard for our network to learn things about sentences if it has to relearn what these sentences mean both times they're fed in. And if we look at the phrase on Monday, now let's say our network learns that if on Monday appears at the beginning of the sentence, it represents a time. Now those weights are only present for the beginning of the sentence. So now if we get it was snowing on Monday, with on Monday appearing at the end of the sentence, it's not going to recognize that, and it's going to have to relearn that fact. So essentially, we're relearning the rules of language at every point in the sentence, which is clearly not the most efficient thing to do. So we want to solve this problem, and the way to solve it is by sharing parameters across our sequence. So once we learn something, like the fact that on Monday represents a time or a setting, we can reuse that fact later on in the sentence. So now we might turn to something like a Markov model type of thing, where we have states and transition probabilities, and we know that if the word I appears, for example, no matter where it appears, there's a 0.66 chance that it's going to be followed by the word like. So here we are solving that problem of sharing parameters. But the key thing with the Markov model is the Markov assumption states that each state only depends on the last state. And this is kind of a problem for complex sequences like natural language or speech waveforms. Because let's say we have this sentence. In France, I had a great time and I learned some of the French language. I knew the word in the blank was French because I looked back at the word France that appears at the beginning of the sentence. But if our model is only looking at the last word, there's no way it's going to be able to guess that. It's going to be a very simple model to try and model a very complex thing like natural language. So now we can kind of see why we need to turn to a different framework called recurrent neural networks in order to deal with the problems that we've encountered, namely the problem that we want to maintain word order. We want to share parameters across the sequence so we don't have to relearn things across the sequence. And we want to be able to model and keep track of long-term dependencies. OK, so a recurrent neural network, when you look at it, is pretty similar. It's architected in a pretty similar way to the feed-forward neural network that you saw in the first lecture. There's some inputs, there's some hidden layers or multiple hidden layers, and then there's some outputs. The key difference is that each of those hidden units is just doing something a little bit different. So let's take a look at this one hidden unit to see what it's doing. So the key thing here is that each hidden unit, in addition to computing a function of the input, also computes a function of its own previous output. In this way, it's able to keep track of things that have happened in the past, which a feed-forward neural network is not able to do. So if you look at the last equation on this slide, the equation for calculating S1, you'll see, S1, to clarify, is the output of the hidden unit at time 1. And that's also known as the state of the hidden unit. So it's really similar to how you calculate the output of a hidden unit. Like we saw in the first lecture, it just multiplies a weight times the input, and feeds that through a nonlinearity. But in addition, it also multiplies a weight times the previous state of that same hidden cell. And it just does this through time. At the next time step, it'll do the same exact thing, take in the next input and the previous hidden state, and calculate a new hidden state. So a common way to view recurrent neural networks is by unfolding them across time. So in this diagram, the orange circle is the same hidden unit, just at different points in time. So you can see that at each time step, it takes in a new word, and it calculates the next output of the hidden unit based on that new word and its own previous output. And it just continues doing this throughout time. And by time, just to clarify, I say time, but that also means if we have a sentence, like the word in the sentence or the point that we're at in the sentence. One key thing to notice here is that W and U are staying the same throughout the sequence. So this solves one of our key problems from earlier about sharing parameters throughout the sequence. Basically now, once we've trained our network and once we've learned something like on Monday represents a time, if that appears at a later point in the sentence or at any point in the sentence, we'll be able to recognize it because we're sharing parameters, and we're sharing our weight matrices W and U. OK, and the other thing to notice is that the cell state, S sub n, at any point in time can contain information from all the past time steps. So notice that the cell state at time 2 is dependent on the cell state at time 1, which is dependent on the cell state at time 0, and so on. So this solves our other problem about remembering information from far back in the sequence. Now, since each cell state is calculated as a function of the previous cell state, we can remember things from arbitrarily long ago. OK, so now I just want to go through some possible tasks that you can formulate with your recurrent neural network and how you would architect the network to perform these tasks. So one common thing that's done with recurrent neural networks is what's called a language model. And what you do here is you take text in some language, like English or French, or even a specific subset of English, like all the works of Shakespeare. And you train a recurrent neural network to model that language. Now, now the output of that neural network will be so basically now the recurrent neural network is learning something like it's learning the rules of that language. And this could be things like grammar, structure, or like the quirks and the language that Shakespeare uses. So this is the output of a language model trained on all the works of Shakespeare. And it looks pretty, like, I don't know, if you showed that to me, I would say that it's probably written by Shakespeare. Okay, so the way that we would formulate a recurrent neural network to model as a language model is by just producing, in addition to producing the next cell state at each time step, we also produce an output. And our output is just generated by multiplying another weight matrix by the cell state. And what it's doing basically is saying at each time step, what is the most likely next word? So given that I'm at the start of a sentence, what is the most likely next word? Given that I've been trained on all this Shakespeare. And it might say, okay, the most likely next word is alas. Then I'll say, okay, now given that I've seen alas, what's the most likely next word? My. Okay, now given that I've seen alas, my, what's the most likely next word? And it would say honor, for example. Okay, so there's a lot of interesting language models that you can build. This is a funny one that's been trained on two things, the King James Bible and the Structure and Interpretation of Computer Programs textbook. And it produces things like, hath it not been for the singular taste of old eunuchs, new eunuchs would not exist. You can see more examples on that link. Okay, so another oh, yes?
How are you calculating the error in a language? Like, how do you say that if the wrong word is, how wrong is the wrong word that's next to the sequence?
Yeah, so I'm actually going to get to how you train a neural network later after this section. Okay, so another possible task is classification. So say we have a bunch of tweets and we want to just determine whether they're good or bad or neutral. And you'll actually be doing this in the tutorials, is sentiment analysis on tweets. So the way we would architect this neural network is same thing, just that we're only producing an output at the end, and our output at the end is a probability distribution over possible classes. And in this case, our classes would be things like positive, negative, or neutral. And notice that we're making the prediction negative based off of the cell state at the last time point. Not off of all the cell states, just on the cell state at the last time point. So you can see that that cell state kind of has to encompass information about the entire sentence. So it's kind of a representation, not just of the last word, but of the entire sentence up until that point. This is a really key idea, this idea of representations being learned in a network. This is a really key idea that I'll get back to later in this lecture and in future lectures. Okay. The final task I want to go over that's pretty common is machine translation. So this is a type of structure called an encoder-decoder model. And that's because there's two different recurrent neural networks. The first is known as an encoder. It takes the sentence in one language that you want to translate. So let's say the dog eats. We feed that into one recurrent neural network. And then we take the final cell state, feed that in as input into a decoder recurrent neural network. Which is pretty similar to the language model that you saw earlier, just for a different language than the encoder sentence. So in this case, it's a language model for French. And given the last cell state of the encoder, it is able to generate a sentence in a different language. Now, this is pretty amazing because it basically knows, it has to get an idea of what the source sentence was about based just off of that last cell state. And like I said, it's able to do this pretty well because that cell state is kind of a representation or embedding, we call, of the entire sentence, the entire source sentence. Okay. So now I want to get into how we train a recurrent neural network. So it's a similar thing as you saw in the first lecture, backpropagation. There's just an additional time dimension. So as a reminder, in backpropagation, we take the derivative of the loss with respect to each parameter in our network, and then we shift parameters in the opposite direction of the derivative in order to try and get to the point of minimum loss. So notice that in a recurrent neural network, we have a loss at each time step. We're not just making a prediction at the end. Oftentimes, we're doing something at each time step and making a prediction at each time step. So because of that, we have a loss based on whether we calculated y0 correctly, whether we calculated y1 correctly, and so on. And we'll call those losses j sub 0, j sub 1, and so on. OK, so it's pretty simple how we deal with this. Since we have a loss at each time step, to get the total loss, we just sum the losses at each time step. And since our loss is just the sum of the losses at each time step, our gradient is just the sum of the gradients at each time step. So let's just walk this through for a particular parameter w. Let's say we want to figure out how we need to change w to make our network better. Well, we want to take the derivative of the loss with respect to w, and we know that's just the sum of the derivatives of the loss at each time step with respect to w. So let's look at a particular time step. Let's say time step 2. So like before, all we have to do is use the chain rule. And we know the loss depends on the output depends on the cell state, and the cell state depends on w. But unfortunately, it's not actually that simple, because if we look at that last term, we can see that the cell state, in addition to having w fed into it, it also depends on the cell state at time 1, which also depends on w. So we can't just treat that last term as a constant. We have to expand it even further, because the cell state at time 2 depends on w in many different ways. OK, so how exactly does the cell state at time 2 depend on w? Well, we know that w feeds directly into it, but it also depends on the cell state at time 1, which depends on w, and the cell state at time 0, which also depends on w. So in order to figure out how S2 depends on w, we have to sum all of these things. And we can just rewrite this as the following sum. But the key thing to notice here, or to understand here, is that we're counting, is that w contributes to the error at all the past time steps. And we have to incorporate how w contributes to the error at each of those time steps. And this is because the key thing with recurrent neural networks is that any one time step depends on all the previous time steps. So any error introduced in the previous time steps affects our time step right now. OK, and this is just rewriting it in a general way, and because this rule applies to any time step. All right, so it turns out that recurrent neural networks are pretty hard to train in practice. And so just want to go over why this is. It's because of this annoying problem called the vanishing gradient. So the vanishing gradient occurs because if we look at this equation, this sum, and this sum is just what I showed earlier about how we would calculate the gradient with respect to w at time step 2. If we look at this one term, we can see that it itself, at k equals 0, for example, is also a chain rule, because we know that the cell state at time 2 depends on the cell state at time 0, but in order to calculate that gradient itself, we have to go through the cell state at time 1. So that term expands with the chain rule into the derivative of S2 with respect to S1, and then S1 with respect to S0. And OK, that doesn't look too bad. But what if we were looking at a much further on time step? what if we were looking at S sub n, which is like arbitrarily far in the future, and we're trying to calculate how the error of w at time 0 contributed? Well, then that chain rule is going to get really, really long. Yeah, so as the gap between time steps get bigger and bigger, as we're trying to incorporate errors from further and further back, this chain rule product is going to get really, really long. OK, well, so what? We need to, if we take a closer look at each of those items, at each of the things in this chain rule, we'll notice that they're all of the form of the derivative of S sub n with respect to S sub n minus 1. And what are each of those terms? Well, this is the expression. You can understand it later or ask me. But the key thing to notice is that each of those terms is mainly made up of w's and f primes. W's are our weights. And our weights start off initialized usually from a standard normal distribution, which is mostly less than 1. Our f prime is the derivative of our activation function, which is usually something like an inverse tangent or a sigmoid. And that derivative is pretty much always less than 1. So you can see we're multiplying a bunch of numbers that are pretty much always less than 1. And that's going to get really tiny really fast. OK, we're multiplying a lot of small numbers together. And what this means is that the gradients from further and further back, basically the errors from further and further back, are going to be contributing less and less to the loss at future time steps. Because of this, our network, and remember that those gradients are what our network is trained with. So if we're training our network but not counting errors from further and further back, our network is going to be biased to kind of capture short-term errors. So again, we're not really, so our parameters are basically becoming biased to capture short-term dependencies. And this is a problem because now we're back at the same problem that I mentioned earlier. If we have a sentence like this, in France, I had a great time and I learned some of the French language, we need to, if we're only looking, if our parameters are basing the next word only off of the last 2 words or the last 3 words, it's going to be really hard to model things like natural language. OK, so now I just want to go over some solutions to the vanishing gradient problem that are used in practice and which are pretty important to actually getting recurrent neural networks to work successfully. So the first thing is the activation function that you choose to use. And this is the nonlinearity that you choose to use. So Nick introduced a couple different nonlinearities, but notice that these are the derivatives of some very common ones. Notice that the derivative of inverse tangent and sigmoid are pretty much always less than 1. But the derivative of the ReLU function, for example, is 1 at any point that's positive. So if we chose to use that one, it prevents f prime from that f prime term from shrinking the gradients. So that helps us a little bit. Another solution is the way that we initialize our weights. So normally, like I said, our weights are initialized based on, they're sampled from a normal distribution or a truncated normal distribution. But basically, that means that they're going to be mostly less than 1. But if we instead initialize our weights to something like the identity matrix, if we initialize our weight matrix to something like the identity matrix, that prevents that W term from shrinking the gradients. The final solution is a little more involved. It's called using a gated cell. So all this means is that instead of having that normal recurrent unit, the simple one that I explained earlier, we just replace each recurrent unit with something a little more complex called a gated unit. And a gated unit basically controls the flow of information through it with several logic gates that allow certain information to pass through unchanged and basically prevent it from being multiplied by basically prevent the vanishing gradient problem. And so some common gated cells that are used are LSTMs, or long short-term memory cells, or gated recurrent units, or GRUs. So I'm just going to quickly go through kind of a high-level understanding of how an LSTM works to give you an idea. It's really similar to a recurrent cell in that it takes in a cell state and outputs the next cell state based on that. But there's just some additional steps in between. So the first thing it does is forget irrelevant parts of the previous state. So for example, if I'm modeling a sentence and I see a new subject, I might choose to forget the old subject because I know that the next verb will be conjugated according to the new subject. The next thing I want to do is selectively update the cell state values. So I can choose exactly which ones I want to update. So for example, if the new subject is singular and masculine, for example, I might want to update my cell state so it knows that, because I know that'll be relevant information to the next verb to conjugating the next verb. Okay, the next thing I want to do is output certain parts of the cell state. So there might be certain things that I want to keep in the cell state that are not relevant to the output at this time. So say I have the word France in my cell state. I might want to keep it there, but not output it, because it won't be relevant to this current word that I'm predicting, but it will be relevant at some future time. In this way, I'm able to hold on to things without them contributing to the loss at that time step. Okay, so again, with an LSTM, we first want to forget irrelevant parts of the cell state, selectively update the cell state values with things we think will be important, and then output certain parts of the cell state that we think are important to predicting the output at that time step. LSTMs solve the vanishing gradient problem and are able to better model long-term dependencies because the forget gate allows you to forget certain information but also remember certain information and let it pass through unchanged without multiplying it by that activation function that shrinks it. In addition, that update step, the middle step, happens by addition, not by multiplication. So that prevents that really long chain rule product from happening. Okay, so I just want to recap by going over the example of machine translation and how it's commonly implemented in practice. So this is the same encoder-decoder model that you saw before with translating an English sentence to French. Now that you know about LSTMs, we can replace each of the recurrent units with an LSTM, and this will give us more power to model long-term dependencies. But you might notice that a problem here is like I mentioned earlier, we're trying to predict the entire output sentence based just off of that one fixed length encoding, the final cell state of our encoder RNN. So this is a problem because, yeah, okay, maybe it'll do okay with a simple sentence like the dog eats. Maybe it can encode that in that fixed length S2. But what if we had a much more complicated sentence or even a paragraph that we were trying to translate? It's going to be pretty hard for it to do that. So what's commonly done, it's going to be pretty hard for it to encode that in that one fixed length vector. So what's commonly done in practice is something called attention. And this basically means we're attending over all of the encoder states. So the feature vector that's fed in to our decoder, that's telling our decoder what the original sentence was about, is not just the last cell state, but a weighted sum of all of the cell states from the encoder model. So in this case, if we're decoding the first word, we might choose to put most of the weight on the first cell state from the encoder, because that's probably what's most relevant. Then when we're encoding the second word, when we're decoding the second word, we might put most of the weight on the second cell state, but maybe a little bit on the first cell state because that might tell us the tense or the gender of the word at the time 2, and so on and so forth. And those weights that we use to create this weighted sum are just learned along with the rest of our parameters in the model using backpropagation. They just become part of our theta. Okay, so now you have a general idea of how to model sequences with recurrent neural networks and why we need recurrent neural networks rather than just a feed-forward neural network in order to model sequences that are kind of dependent on each other and could be variable length. We kind of went over ways to build models for different types of tasks like language modeling, classification, and translation, and how to train them with backpropagation through time. And in addition, why they're hard to train because of the vanishing gradient problem and how you can solve that. And finally, the last thing we talked about with the weighted sums is called using attention mechanisms. So there's lots of more things to do with recurrent neural networks. There's tons of applications extending these models from just modeling sentences to things like time series, waveforms, complex language models to generate not just a sentence, but to generate like a book even. Models to generate code, controlling cars and robots. Actually, I think that Audi is developing like a self-driving car that tries to park, or sorry, a self-parking car that tries to park itself using LSTMs to model the way that the car will move. Predicting stock market trends, summarizing books, handwriting generation, et cetera. The list goes on. So yeah, I hope that you have an idea of how to model sequences now. We're going to have a short break, and then at 12:30, we're going to come back here to work on the lab. And there are snacks and coffee set out outside, so you should hang around and chat with your classmates.